I'm happy to be here. I've been working in this area for 30 years in sustainability. So when I got the call, like, what do you want? You know, want to give a seminar? I'm like, what do I do? And I was like, okay, bioinspired design. I can't do because Mark Weisberger is going to take that. So I ended up with this topic, which really we've been working on for 10 years. Many people don't know about it, but we've been working on it. And I've skipped for the next slide because that's me. I'm from University of Twente and so on. But it started kind of like with this thing. If you all think, one of the things that I do is not just like work on design of a thing or a gadget. We look more at systems, sustainable systems. And this is kind of like classical. You got your house and your car. This is typically when it started in the 1950s, your ranch house with GIs coming home. You had your big old car there. And people design a car, people design a house. Architects and you get mechanical engineers on one hand. And they only share the car in the garage, and I gotta basically get rid of this little thing because I can't really see what's in there. Here we go. And 50 years later, this is like from the 2000s. My son loves this house, loves the car, a Lamborghini. Basically the same thing, right? You only share the car, you only share the garage and the occupants. Those two designs only share the things. Now in 2011, actually 2012, we got a call from Ford. So I say, hey, Bert, we want to do something neat. Can you guys get a team together to look at something we call the house of the future, home of the future? And then it got rebranded to a thing called My Energy Lifestyle. Because that actually, what you see in the pictures, was a C-Max, a Ford C-Max Energy with an I, not with a Y. This is not a spelling mistake. This is actually branding. And they say, we really have this plug-in hybrid. And now we get this idea that we have like the home and the car actually start connecting. They're sharing the same fuel, electricity. So what can we do with that? And Fried Algenbrew, as many of you know, Fried, he unfortunately passed away a while ago after he only got retired for 1 or 2 years. It was really sad. I'm not going to, everybody in the room, retire before you die. Don't die. Immediately after retire, please don't. Okay? Yeah. But he helped us with that. And we started talking about like, how do you model a home? How do you model a car? How do you model an EV, etc. And we did this with Ford, and they actually really, this was really innovative at this time. They basically had a car company starting to call up a appliance company, Whirlpool, and say, hey, can we do something together? And SunPower was a photovoltaic company. And they're like, hey, can we do something together? And Eaton is an electrical system company. They make lamps, lights, and so on. Can we do something? And Infineon was like a switching company, electrical components company. And the person actually who started this at Ford, Mike Tinsky, is now professor of the practice of mechanical engineering. He might actually be online. But he had this, I guess, brilliant idea to go across basic industries. Not just have the car guys coming together. He said, like, let's talk to the non-car people and get a conglomerate together to see, can we do something together? Can we have smart appliances? What if we did smart appliances? What if we did photovoltaics? What is the benefits of having the sum of the parts and just simply the parts, like parts together? Now we had a job to like figuring out what would be the benefits. And this was branded My Energy Lifestyle. I checked, the website has disappeared, but it was featured at the 2013 Consumer Electronics Show. Now, that is a big deal for computer scientists. I was kind of like, oh, why whoop-de-doo? But actually, it is a big deal because you basically get out there and this basically was featured. This are results. The results at that point, and this is like very quickly before we go in more stuff, we had different scenarios, but we still do that today on new models. There's a baseline, and you can see like 1990s appliances. All this is based on a retrofit. We're going to retrofit a typical Ford customer home of 1,700 square feet, in California, of course, because California is way ahead. And actually, we're going to do one more thing. We're actually going to give away a package with a car, new appliances, a solar panel, etc. We're going to give it away to 1 or 2 deserving customers, and they have to basically apply for it. But what you see is like we did scenario 1 baseline, then we had no electric vehicles, but we added PV, new appliances, add some smart control, time of use. Then we did an electric vehicle, etc. What do we do? And we developed the Fried Algebrew MATLAB model. Fried had these models that he developed where you actually had like emissivity for windows. You had basically like a finite element analysis model of a house. If people walked into a room, then the temperatures would go up, the AC would pick in. Really was every 5 minutes, it was updated, etc. So it's a big old model at time series. Now at that point, what we got to was these kind of graphs and the big blue one, this one here, where's my mouse? Where's my mouse? Okay, well, the light blue thing is hold on, let me get a mouse out because just want to make sure. The light blue thing is actually, if you start taking an EV and you got rid of the gasoline, this is basically right here. That's basically your fuel avoidance, your CO2 and energy avoidance from basically going from away from gasoline and body energy, etc., to electric vehicle. This is a gasoline vehicle, and you see this is actually two vehicles. We got rid of one vehicle, and you got to an EV. The bottom line is you got some enormous savings, etc. Not so much on the appliances, basically swapping the vehicles out. That was then. Interesting, not so fun fact. Marilyn will be kind of like appreciated Marilyn Brown here. The rebound effect. Literally, what happened when they handed out the first retrofit package to a homeowner? The homeowner said, "This is great. I can save some money. Now I can run my hot tub longer." That's not what you want to hear if you want to save energy, that somebody can run the hot tub longer. But that was literally like what they said. That was then. Since then, that was 2013. We've actually, this My Energy Lifestyle for short, MEL, we actually had, now we're now in version 8, literally. We had 2, that was the first one, we changed the light to LED, and wiring to DC only. We had DC wiring instead of DC house, so you had to get the AC, see what the benefits were, play with the battery electric vehicle versus the plug-in hybrid electric vehicle. MEL 3 was basically this previous 2 versions. Now we started talking about battery storage, literally lead acid batteries. What can you do with that? Didn't work. MEL 4, I got a slide on that. Microgrid, that was an interesting one. Jamie Cornell worked on that with Friedaugenbrew and I again. Then we had a MEL China, where we started doing the same thing, but Ford said, like, let's do it in residence in China. And actually, Lily Friedaugenbrew and I had to go to China. We flew out on Wednesday, landed on Thursday evening, had a meeting on Friday, realized that they had no clue what we were talking about, canceled the meeting for Saturday, went to the Forbidden City, beautiful day, could see the mountains like I've never seen so beautiful, and flew back on Sunday. You don't want to do that. But it worked. MEL 5, we started looking more climate zones. MEL 6, now we started looking at, like, there was a house, a Renew house in Purdue, where they actually had real data and really retrofit. And the guys who worked with then and Ford said, like, let's see if we can do some calibration. Well, you can see the dates starting to happen. I forgot, that's 2019. You know what happened in 2019, 2020. We wanted to get the data, and then of course COVID happens, and we wanted to integrate. They wanted the battery in there. The battery didn't get delivered. It was all kind of, and whenever you have sensors, you know there's going to be sensor errors and things that worked out not so good. So that got canned, but now we're in 8. So what you're going to hear today is more on what's called the My Energy Lifestyle 8, which is building on all this stuff, and I got a slide on that. But here's, first of all, the microgrid. This is so like already a primer that some of the things that people talk about, what we found out is they're not that great. We actually had 10 of these homes that we had in the My Energy Lifestyle, the 1,700 square foot homes together, with different variety of people attending, and all of which basically ended up with giving a net savings about max about 700, 800. If you started squeezing it, you did some other backflips, you got maybe like $1,000, $1,200 savings per year. And Fried was like, "Oh, that's really good." I said, "Fried, for $100 a month, and it's not even in the infrastructure, the cables in the ground to connect the houses, we could really do that." And he's like, "Oh, that's, yeah." And Fried is Dutch like me. He was always like, "Yeah, you're pretty blunt. You're from the east of the Netherlands, right?" Yeah. But the microgrid thing was, it's not so big as some people make it believe. I'm not saying make it believe, but there are savings, but it's not that you say, "Wow, I'm going to change my entire lifestyle," compared to like just adding PV to your individual house. Connecting houses didn't really add up so much. So where are we now? We're actually, I lost count, we're at 8 plus. But really what we're going to talk about today, what Stephen Johnson, who's online, I think I saw his name there, who is working on, is like really build on these things and create a simulation model that really is geared towards the homeowners who are prospective EV owners. Literally, I think the goal is that to have something on the web that somebody is thinking about, I'm an EV owner, plug in their utility data, their loads, etc., and kind of self-assess and optimize the greenhouse gas emission financial benefits. If you have an electric vehicle, electric vehicles plural, like your wife might have one, yourself might have one, basically, or your kids might have an extra one. So, hold on, excuse me, that's my meeting reminder that I'm not going to attend. Excuse me about that. This HES, home energy storage system. And then you do the V2H, the vehicle to home and vehicle to grid controls. And if people start playing that, what can it be? So that's basically what I'm going to talk about today, what we're working on, what Stephen is working on. And here's basically a broad model overview. Again, I'm not going to read all these things, but what you see here is basically like electric vehicles, what's blue, what's kind of orangey is what's called the source, electricity provider, the grid utility. PV array, they provide electricity. Then the pink, dark pink is the household. That is basically a sink. That's where electricity goes to. And then there's the blue things that can be both sources and sinks, the home energy storage system and electric vehicle. They can actually, electric vehicle needs electricity to be charged, but nowadays they are getting to the point that they can also provide electricity. By the way, anybody telling you about 5, 6 years ago or 7 years ago saying that electric vehicles could provide electricity to the home were basically smoking something, because the cars were really not equipped yet to do that bi-directional flow. They could only get one directional flow. That was all hypothetical speaking. And even now, I can tell that you see ads for cars and they do light up the house, but that's really for emergency backup, because cars are not NEMI rated. They're not UL rated. They don't want to certify it. So any electrical equipment has to be UL lab rated, what U stands for, and also have conform to electrical codes. Many automakers say, we're not going to touch that. We make cars, we don't make electrical components. Now, that may change in the future, but you have to be careful when you think about cars can just plug in and power your house, no big deal. So there's a little bit of like detail. We still do.
Is the insurance on batteries now still voided if you do use it for a V2B?
Don't know yet. We'll get to that. So so anyway, the model is still the same, 5-minute time steps. And here's what we're trying to do. You want to do performance analysis of all these components, look at some performance metrics, the components of the cost savings, the EV, what value can you generate if you have an electric vehicle, the whole system. Do you have a payback? And then also like look at for many localities to select it. So it's pretty comprehensive because it's built up over time and there's a lot of things you can tweak. It used to be in MATLAB and Stephen converted to Python because the MATLAB literally would run hours. The Python now runs in minutes. It's still like 10-15 minutes to basically do a whole year worth of cranking, etc. We do have a lot of model data. This is to give an idea what goes in. Right now, we used the US utility rate database for all the utility rates. That gets basically scraped by locality/zip codes. There are some simplification. Policy-wise, you do wholesale rate, and he sets it at 3 cents per kilowatt hour. There's net metering policy, but all the time of use rates basically get loaded, and the peak times, because different have little peak demands, that the rates go up between certain times of day. Again, Atlanta has a different time of use rate than, say, Los Angeles. That's all in here. This all gets basically loaded in massive spreadsheets, and basically get loaded based on what zip code you're running, or the nearest rate by nearest zip code. There's a word called reference city, because if you, for example, are in, let's say, LJ, Georgia, that may not have a rate in there, and so they pick the nearest big city, nearest rate that it can actually allude to, etc., and use that to sort of like run the model, etc. There are also a bunch of EV inputs. So this particular thing to use it for right now, we have the Ford F-150 the results. I'll show some results that we basically used the F-150 Lightning for that has a 131 kilowatt hour battery, but that you can change. We run it for the Focus battery electric vehicle in the past, the smaller battery, etc. We can actually run multiple EVs now as well. Now single EVs used here, and also driving patterns like commuting distance, 20 miles per day, one way or longer. Those can all be tweaked. Departure return times with the microgrid, for example, we had like stay-at-home mom, retired couple, double two income family, and you can have these different driving behaviors that will actually also affect when is a car available, not available, EV available, etc. And then we have things called vehicle to house V2H discharge limit, because not everybody wants to discharge the battery completely of their EV. This is all the EV. So like, because they want, like, I want to be able to go to Kroger and I want to be able to hop in the car and drive. And for example, the 100% limit means like you don't allow it. You want to keep your battery state of charge 100%. And we'll see actually that these batteries are getting so big now that you actually like, you don't have to worry about this stuff anymore. Now, a little side thing is that we actually are including some real data if we can. This is an EV charging curve, a representative curve. And typically when you charge an EV, you have 3 stages, like ramp up. That's a big old spike over here. This is over time. You ramp it up. And then there's a steady state. You see some wiggling going on. This is actually from a real vehicle, steady state. But then the big thing is what's called the trickle down. When it's getting full, the battery control module starts slowly building off the charge. So if you like think about charging an EV from the grid or from your solar array, you might say, okay, I can pump 10 kilowatt in there and power very fast. Not so fast, doesn't happen anymore. When the battery gets full, it starts limiting how much you can charge. So that's doesn't affect things that much, but it is one of those things when you start looking at the 10% range of using the battery, it starts basically like you may have like an issue like really putting it in there because you need more time. So the power for charging goes down. The other thing that we started building in there, this is something new and also still in develop, is battery degradation. Many of these models that we've seen in literature are saying, oh, they assume kind of like that you don't have any vehicle to home. If you start charging the EV and charging the home with it, etc., that there is no real cost for your battery on there. Actually, there is a cost because we all know, like, if you start, like, charging your cell phone, eventually over time, it starts degrading. Now, we have a very simple model implemented right now, very conservative. It basically says, like, if you discharge, if you basically use, say, 100 kilowatt hours as an energy and you draw it from your battery, that energy, well, how far could you have driven with 100 kilowatt hours in miles? And these numbers are known because it's the efficiency. They'll post like you can per mile, you need 100 miles, you need so much, or you basically look at the range. You have a 131 kilowatt hour battery in a Ford Lightning, you can do about, I think 300, let's say 300 miles per. So you know that basically for every mile you use like a third or half a kilowatt hour. So you can sort of say, so if you use 10 kilowatt hours for your house, we could argue you actually drove 2 miles or 3 miles or a certain number of miles you actually do. And if you then start adding it up and you say, okay, well, what if my battery had a 100 miles warranty, 100,000 mile warranty? I drove real 50,000 miles, but I also used 5 or 8,000 miles per year to charge my home. That's a warranty issue potentially. Now, this is still controversial, and this is very, very, very conservative, but now you start also seeing that. And then you can calculate now, do a little bit of cost of degradation to sort of see, hey, how much is it going to cost me to use my battery for charging my home versus using my battery to drive? And am I getting out of warranty now? Is it degrading? Do I need to replace it? Etc. And so you see lifetime numbers we use for now, 100,000 miles and a battery cost of $170 per kilowatt hour. That's the initial cost. And use those numbers to depreciate, basically. You're doing that. Now, we'll come back to that later on. Then we have household data. We either use the user, the consumer can put their own stuff in, flat yearly usage, and the model finds the best from the NRL's Restock load database. It's a house load. It basically starts matching like how big is the house, where you're located, trying to fit it. If you have the user provides a monthly bill, that's also nice. But because we're on the, you have a high time resolution, that's great. Sometimes you can get back to the hour. In this case, because we're running on 5 minutes, we do interpolate, and so I get it to the 5 minutes and see how it can go there. Now you might say, why are you still 5 minutes? Like, well, it's built up that way. We keep it 5 minutes. It does allow to like do these fun things actually, because fast charging, discharging, and also like matching with real load data, etc. Grid emissitivity, they come from standard databases that are now way better than when we started like 10 years ago. 10 years ago, this was like hard to find. Now it's like out there, you can load it, NRL's database. So again, you can have it here and you can again match it to the season. And again, we do some interpolation to so like say we do the 30-minute resolution that they now have, we reduce them to 5 minutes for the year. And it's all basically, unless I say otherwise, it's all based on a year data, annual basis. And the system size for the PV. And now we assume right now 18%, that's the current default. Of course, you can tweak this now. You can get it now, they said they're over the 20% already. And $1 per kilowatt installed, defined by state, that's one of the numbers you can tweak as well. But those will give you an idea about these things. Same with home energy storage system, the default capacity. We have an optimization strategy built in, where the storage system, if it's present, will charge up first with solar during off-peak, so it can unload during peak. So we use the battery to select when you have a peak, when the prices go up, that's when you use the battery. That's when you don't want to use the grid. And that's why I said the second bullet, the home storage system will prioritize peak and mid-peak tariffs based on the electricity rates. And then the user can define some flat, etc., and so on. But if net metering is wholesale rate, then basically you don't want to have you basically want to capture more solar energy for later use and selling back to lower. So basically net metering versus wholesale make a big difference. If you have net metering, meaning like the company, the utility company takes your electricity from the solar array and basically like you get the same price for it almost. You want to pump as much solar as you can back and offset it. But if they don't have that, the wholesale, then you just don't want to sell back because you only get 3 cents per kilowatt hour for it. You want to use it at home. That's when typically your storage systems get bigger because you want to store it for later at night use and even evening use. Whereas if net metering is like give it back as fast as possible because so on. So you see these numbers changing. All right, so here's a little bit of methodology. It's too small to read probably, but there's different things that come in there. There's a house, grid utility, home energy storage, and PV, these are the components. And then every 5, this is basically the loop here. Every 5 minutes, this goes through the loops, does an energy assessment, checks, updates the storage strategy, check the EVs, how that storage system is going. So is the components like who should be a sink, who should be a source, does the energy transfer, update cost of use, and so on. House energy assessment, how much energy do we need? What's the PV that we actually output that we get at this point in time? Because if it's right now in Atlanta, it's cloudier maybe than in summer. What do we get? What's the current electricity cost? Based on that and the loads, say, okay, do I need to discharge my home energy storage system? Do I need to charge it? What's going on? And so on. And then I move to the check EVs. Is there an EV presence? Is the state of charge? What is that? If it arrives, when is the next departure that we can select? And this is where we right now have it hardwired, but you can sort of see when you do start doing machine learning, artificial intelligence, that you can start learning this from certain behavior and start predicting this. Goes through what's called the component sorting stage, which is a source, which is a sink. House is always a sink, it's always a load. PV and grid always a source. But then the home and storage system and EV, if both are present or one is present, then it starts figuring things out. If it's 100%, then you cannot be a sink. If it's at the lowest level, then it cannot be a source, then it needs to be charged. There's peak off peak charging deadlines. And the sinks basically go priorities like first run the house, then charge the EV, next charge the home energy storage system. That's kind of how it works. And PV is always first from a source because the cost is 0. We assume that you basically the capital investments separately. And energy transfers, again, similar thing. You see like how they basically provide source supply energy based on the amount they can provide. PV is limited to solar. HES can discharge only a limit, 7 kilowatts. That's typically the high end we use for power point of view based on the Tesla Powerwall. We at one point did actually we did the study also with 25 and 50 kilowatt DC fast charging. Basically, you had a big old battery sitting in your house, and then from 50 kilowatt, just like boom, ram it in there. Now the house never needs 50 kilowatt. When people talk about 50 kilowatt, that is to charge a car. And 100 kilowatt is basically like 150 horsepower roughly. That the main. So you still like your car has over 200. All your cars have over 200 horsepower typically. That's over 100 kilowatt, way more than 100 kilowatt. So a house runs not even at 10 kilowatt typically. So it tells you like already like how different these things are. And certain transfer bin, you can't. The EV is not allowed to provide the home energy storage system, grid to HES, peak current, yada, these kind of things. So all that runs to a cost of use. We get basically a cost for, bless you, $4 per kilowatt, and that helps us on deciding like, hey, what is the current cost of charging the home energy storage system? What is the home energy storage cost of electricity for charging the house? Should we get from utility? Yada, yada, yada. And you basically get this equation here and basically updates the cost of every source by the 5 minutes to sort of see what makes sense. What do we decide? Same with CO2, we do the same thing. And after the last things that we break the whole thing in the monthly breakdown, you get a total tabulation, etc. You get your system cost, component cost, EVs, the miles driven actual, the miles simulated, vehicle to own, and a degradation. Now, to run this, we're going to show you some results. We have Stephen has actually run this model and made many results, and the others changed, etc. And of course, like the utilities change, the results change. So for this particular set of slides with the following input parameters, we use Atlanta, Phoenix, Los Angeles, Portland, 4 cities, do a little bit, compared to a baseline a little bit. And here are some of the numbers that we come in there. PV, we actually varied from 0 to 10 kilowatt. Homeowner storage system 0 to 40. We'll show you some nice graphs. You can start see this in 3 dimensions, the cost. V2 is limits, 170, 50, and the commuting 20 miles and work. So we assume somebody's working. Yearly use is typically whatever, if it's on-space out 11,000 kilowatt hours. Let's use average, but we'll have some numbers also with some higher things. So that's the same model again. So, and here's some more data. You can install cost, yada yada, specifics. And here you see, for example, solar cost and the bottom tax rates. All this stuff goes in the emissivity rates. We are pulling those. We try to be as exact as possible. If we can sort of get it to a nightly or an hourly. Doesn't work that way, as we all know, but we're trying to bring that in to sort of see where's the dirty power, where's the clean power. Of course, you can also change the whole behavior by saying, I want clean power, and I don't care how much it costs me. But that's not typically what people want. But we do keep this in here. And at the time of use rates, we see these over here. And these are kind of like, we use that kind of standard for these cities. The worst city I think Stephen ever done was Austin. It had many time of use rate, really out like a power rate. Did that, but it's like, these are the simple ones. So what you get now is these kind of graphs. And this is, for example, system cost efficiency, the total system cost, basically money saved versus money spent. So what you see here on this particular graph is the system cost efficiency. Higher, of course, is better. 0 is better. And here we have the storage size versus the PV size. Now, clearly, if you have no storage and no PV, you don't save much. And the further it goes up, the more money saved you spend overspent. And you can kind of see already like, hey, well, wait a minute, this is Phoenix, system cost efficiency. It's starting to favor like a bigger PV system gives you a higher efficiency, cost efficiency than, say, a higher storage system. And in fact, you see the storage system, some storage is good, and then it starts tapering off. It basically doesn't pay anymore. It actually is detrimental. So you start seeing there's some sweet spots here in suddenly things. And here, the axis change something. Here's another one from Phoenix. The difference here is net metering versus wholesale. This one is wholesale. This is net metering. Net metering, you can pump back to the grid, and you get basically the same amount of money, almost the same amount of money. There's a little fee associated for if you the electricity you buy versus that your photovoltaic array pumps back. So more photovoltaic makes sense because you get more free electricity. But if it's wholesale, meaning you only get 3 cents per kilowatt hour, now what you're seeing is that the system says, no. We have a sweet spot with the PV array where it actually is covering the loads during peak. You don't want to get too big. Bigger is not always better here. And same with the home energy storage system, the battery. Bigger is not bad. And that's kind of like a big thing you see. So this is like one of the things that we see with these models that you can play with. If you use it for like different towns, the top one is Phoenix, the bottom is Atlanta, you see completely different behavior. Phoenix, you get, this is again net metering. Phoenix, you get really good solar. There you go, big solar. Atlanta, again, you're like not so great. You get the whole axis, by the way, is lower. This is like 0.08. This is 0.04. You see, like Atlanta, you get much lower efficiency, much lower return, basically, certain returns. And again, PV home energy system, you can select basically optimize it a bit better. Come on, here we go. And similarly, you can do the CO2 savings per year. There's a, I missed a slide. No, that's it. Okay. It basically shows like we can run with different PV arrays. This is basically like solar size, emissivity factors by the grid. And you see here, for example, 0, here you get a negative. For Portland array is clean. And you can see here basically the bigger the array, you start getting CO2 savings. But again, we didn't put it in a graph. You can probably see a similar graph that it starts plateauing at a certain point. When it's negative, you might you get system losses because these systems do have losses that you basically you need to supplement with still energy, and you might accidentally need to charge with grid energy is a little dirty, and so you basically it's not better than the baseline. Here's an interesting fund. This is the EV cost avoided. This is like the amount of money you save by having an EV. So if the electric vehicles start doing the vehicle to home and starts helping you with basically storing electricity or having electricity available when it's a peak period and it starts discharging in the peak period. Now, if you have a battery system already in your home and now you add an EV, you can still like say, well, you may have a little overkill. So it becomes, again, the previous slides like don't necessarily get the biggest, baddest battery you can get. The same thing happens here. Now it's like the benefit of having an EV is getting less if you already have a battery storage system in your home. Why would you have an extra battery, especially if it's big? And what you can see here is that the EV cost avoided, like the amount of money you save by having an EV, starts rapidly decreasing by the size of the home energy storage system that you have. And the PV size as well. If you have no PV, then it makes sense to have your electric vehicle also helping you save money during peak periods. But if you start having a solar array, then a solar array starts working during peak periods, typically in the middle of the day, to save the electricity. So then, even if the electric vehicle is at home, its battery is not really needed to cover your home, instead of because your photovoltaic array takes care of it. And so you see that these benefits of having an electric vehicle at home start decreasing very rapidly depending on the home energy system size or the PV. And even then, if you don't have a PV, notice in the axis, $200, $140, that is per year. That's having the, for this particular run, that's having the cost, the amount of money you save by having an EV and using it for peak things. Only about $10, $20 a month of savings for that. It's a little bit like, yeah, not great. And there's another one that's kind of like, this is why we start getting controversial. If you, Stephen calls it the V2H effectiveness, this is where you start putting in the cost avoided versus the battery degradation costs. Remember that very conservative model, like the battery starts driving miles basically and costs you a certain amount of money over time because you have to replace the battery. And you see that this starts really dramatically, rapidly going down. Less than one indicate that V2H is unprofitable. You want to have basically like, if you make $200, you don't want to spend $300 on cost of battery. So anything greater than one means you're actually saving money. Well, all these numbers here are lower than one. It means that you have a much bigger battery degradation than you actually save from doing this. Controversial, we have very conservative model because the one thing you can say, like if you run a car, you run with 100 kilowatt discharges when you hit the throttle. A house, you never hit 100 kilowatt. You maybe hit 10 kilowatt of power. And so it's like these batteries are high power. So you basically, we were saying like you probably don't have the same degradation. That's why this is extremely conservative, but we don't know it right now any better. We do know that some of the car companies are starting to look at this more carefully and see what's going on. But you do know when you charge, if you start with like, if you do a Tesla charge, you start charging with they're talking about 500 kilowatt. This is half a megawatt to on your charger. That's when I don't want to touch this thing in the first place anymore. But that's when your battery starts really like cooking, etc. You have to be very careful. So the same with the factors here. We see that like if you look at Atlanta, for example, you'll lose money. And a couple of solutions, of course, increase the battery lifetime, decrease the battery cost. But that things like break-even life, we have not done it. But all in all, kind of these sad things like it may actually cost you more money to run the battery than actually you get out. Another result that is actually like you can do with this is to sort of look at the peak shaving efficiency. It's a different way of looking at the optimization. I have a table next where I showed some numbers. But you kind of see like the percent of peak period, which is really where you want to do it. Peak period when you pay more, covered by the system below the grid. And you can see here again, this is like 0, the PV array size versus the home energy storage system. Versus the efficiency, you see it start plateauing here pretty quickly. And somewhere over here is probably like your sweet spot. It turns out that if you start looking at all these numbers, you're roughly looking at 5 kilowatt PV array and maybe a 10 plus kilowatt hour storage system, maybe 20 kilowatt hours. You don't have to have big systems, what it comes down to. 5 kilowatt solar array seems to be covering a lot of things already nowadays. And you see these, so this is what we can do. You see definitely different from Portland versus Los Angeles, different behavior per city because of the solar is different. You see that happening here. And if you start looking and straining your eyes, we can of course shame, but you can actually see like when you have a yearly load of 11,000 versus 15,000, the baseline saving, the different rate policies, and you start playing with different arrays like PV array, 3 kilowatt, 4 kilowatt, etc. Different home energy storage systems. This is the size. We do 40 kilowatt and 20 kilowatt. These are kind of the optimum systems where you get to, and you can still like see what you see 20-year values in this number. It's not the payback, but it simply says over 20 years, what would this system pay me? And if you're negative, like in the center of Atlanta, where's a wholesale rate negative, that means like over 20 years, it actually still cost me $487. That doesn't mean it's not going to pay. So it turns out the payback period is 22 years. That's when you break even. But the system here in Los Angeles, they say over 20 years, it saved me $11,000. But if I had a bigger system in Phoenix, but here if I have a higher load, this system was slightly bigger, actually would save me a lot more. So 20 years is basically a way of saying apples and apples. We can see over a 20-year period, it's kind of a net present value with all the interest rates. So I do a comparative analysis. But you can have these kind of like things. Now, there's this clause here because California now has a net metering 2.0, non-biased price loop charges. Apparently, then the thing gets even worse, net metering 3.0. And these numbers have no V2H, no EV, V2H in them. So, because we just said like, that's nothing.
Interest rate of 0.
Interest rate of 0, yeah. Yeah. Because arguably, if they all have the same interest rate over 20 years, you still should get the same, you still get a similar, not the exact number, because the interest rate of 0.
But
the
the
difference.
payback would just look much worse.
Yeah.
With-
Yeah. And so, so we kind of like, again, if you're a homeowner, say like, whatever, but if you put your money in the stock market does really well, then.
Just a dumb savings account.
Well,
So
yeah,
much-
it's, we can, but I think one main takeaways, which we'll get to what value is mainly like, you're not saving that much money. Let's put it this way. You save money, but the sweet,
You're not.
what we found out the sweet, if you want to do like, and again, this is why actually way back 10 years ago, it was called My Energy Lifestyle for a reason. The reason was that people, if you buy a battery electric vehicle in those days, they were really a lot more expensive than regular cars. They're still more. PV arrays, all this stuff is expensive. When you start doing that, the folks at the automakers, at least at Ford, quickly realized you're actually making a lifestyle decision. It's not just about the money anymore. It's really about beyond the money. Now, clearly, then you talk about a little more upper middle class, etc. But it's really like some people want to change, not some people, the people who do that really think about changing their lifestyle. It's like, okay, I stop eating meat, I'm going more vegan because A, it's better for my health, etc. It's not necessarily for the money, it's just for another thing. So that's what it comes down to. So based on that, if you wanted to go that lifestyle, as I said earlier, what from all this stuff we've run so far, sweet spot PV around 5 kilowatt nationwide. Even in Atlanta, even in Phoenix, again, it can be higher. Tennessee was higher side, higher solar availability. But if you go over 10 kilowatt, you kind of like, what are we doing here? Your house, unless you have a massive house, many square feet and loads, you really don't need it. If no photovoltaic is present, then yeah, a 5 to 10 kilowatt hour home energy storage system would be worthwhile depending on the peak rates. Definitely have some batteries. So like, hey, I'm charging this, taking cheap energy at night and doing charging my home during peak periods. But even then, if you think about simple math, you buy even like at 1 cent at night and you save, say, and it's 30 cents in the peak hours, you basically save 29 cents. If you do 10 kilowatt hours, that's $2.90 per day. Over 300 days, you get $600 per year. Well, these systems typically still cost about $5,000 or something like that. So it's still, you're like, why am I doing this? So that's why we're talking about actually about second use batteries as well for automotive. If automotive batteries are old, make them stationary. Not a problem with that, but you can do that. Cable net metering, home energy storage, don't use it. If we ever go in Atlanta to net metering, if they allow it more, then like don't have a storage system, just put all the PV back to Georgia Power, and you get basically more of it, unless you want backup for power. So that's what one takeaway. There's another reason why people want these systems, power outages. But if you start looking at like how many power outages we really have in the United States, you'd be surprised how few there are. It's like, ooh, it happens. Well, we have a house in Florida, got hit by Michael. The power was out for 4 days, and then it came back on. You get hit by a Cat 5, well, not direct hit, but a Cat 5 hurricane came by. Only out for 4 days, and then the AC started running, and the water was out. That's another story, but you're not out every other day or every week in North America anymore. It's not happening, but still it can go. If you have an HES, forget about EV vehicle to home. It's really not really that worthwhile. If you want to do electric vehicle to home, don't have any PV, don't have any home storage system, then it starts making sense. Again, you have battery degradation. But the other thing is that the vehicle has to be present, has to be available. So if you have two EVs, which we've all as well, then you can do that because one EV is the commuter. Let's say the breadwinner is gone, stay-at-home parent is at home. There's an EV at home. It can serve this purpose as well. And basically, and here's another thing: EV battery. This is completely different from, like, say, 10 years ago. The EV battery may at best have covered 40 kilowatt hours, 30% of a full F-150. 40 kilowatt hours, if you remember the old battery electric vehicles, that was the whole battery. The Ford Focus was basically, I think, 30 kilowatt hours or something like 40, close to 40. If you had the reserve that they never published. Nowadays, that's like, okay, what do you do? That's a third of, it's like a third, 30% of a F-150. It's a third of a Mac E. It's like not even like a third of a Tesla anymore. So you start getting these things. And it was like this big, however, EV battery irrigation to be determined. You got to think. So some improvements. I'm going to wrap it up here. If I have questions. We look at the economy of scale. We have flat numbers in there for PV side, PV install cost. What are the economies of scale? Better locality specific installation cost for PV and HES. So that some of these numbers here are based on, like, there's an install cost included. Well, of course, if that changes, some of these graph change as well. Improved optimization, sizing for the stores. The sizing, we can already do sizing and show you. Just look at the graphs roughly, but the control is an issue because we have some simple rules. But again, like if you start predictive weather, you start doing weather patterns in there, and like you start getting power rates in there. Now you start maybe having more advanced control. You can always have more metrics, average kilowatt hour for V2H, etc. More recent EV charging curves. We have a curve in there, but it's more like a generic curve. It's not a linear curve. It's not like a nice curve for each EV model, but that's marginal. But again, if you're only looking at about 10% using the battery, you do have to worry about that trickle down. It's how much power you can charge with. The battery degradation, that's one that we really starting to think about. And of course, we have to talk to the dials and the camera, see what happens here there. But that 10 versus 100 kilowatt is a big difference. So it's probably not the same. Now, down the road, this model, this already works pretty well. One thing we learned is like bigger load, more savings. So can you look at commercial buildings? And this is where fleet owners come in. That's not the reason why we built this model. This was really more like for the automaker, for consumer facing, ideally, the stakeholders. But if you are a Georgia Tech or you're a UPS or a FedEx or Georgia Power, etc., and you have an EV fleet, or you sort of like have accidentally, or you can tap in the EVs that your employees actually plug in or bring to your building. What can you do there? You may have a bit more V2, and I put the H in question in quotes there because it's not home anymore. It's more building, more V2B, V2 building, not necessarily V2 grid, because you kind of don't put it to the grid, put it directly in the building. Those are the big difference, because the utilities are actually still in many ways a little bit of the bad people here. I'm not supposed to say bad guys, but all the bad females, but like the bad people, because they really, the wholesale rate really, really, really low for 3 cents per kilowatt hour for what you do for it. But people talk about, oh, if we have the utility, you put your EV on the grid, you can get some money for it for frequency regulation, for load sharing, yada 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 yada. Well, the big question that also the automakers have: what price should utilities really pay for that? And would you sacrifice your battery of your EV for just helping out the utility? Probably not. How much would it be worth for you to sort of like have somebody tap into utilities? The same as saying, how much would it be worth for you if somebody starts using your cell phone for a little bit of data transfer? Not much, we should a little bit. Like, well, wait a minute, how much data I actually transferring on my cell phone plan? What are you actually doing with my cell phone? Show me the numbers, really. And that's really what we're talking about here as well. So that's what the next frontier is really that. So that, I want to thank you for your attention. Gratefully acknowledged for Motor Company and its past, present collaborators. Mike Tinsky started it all up. We had like Jacob Matthews and other people who like really worked on this for many, many, many years. And the students, Ben Lee, was interesting. Actually, I just connected with him like last week, as he turns out he's now in Germany as an alum. He was working with Chris Bras and Freed and my analyst, Zach Morris, then he Boston, works at Ford now, Jamie Cornell, did the microgrid, Reed Spence, Jacob Rotai, German, Guillaume Michon, and Stephen Johnson, who can answer all the legal questions you have, you want to know about. He is actually programmed this thing in Python for MATLAB. And I put the disclaimer on there. Any opinions, not from the sponsors or the state of Georgia or the National Science, we don't National Science, it's the university, etc. So that, questions?
Good. Online as well, if you want to raise your hand, we'll make sure we'll contact.
Yeah, Maryland was first.
Yeah. So I'm curious about the development of markets for bundled products that maybe involves EV, might just be solar with heat pumps and you get the EE assets in there. In Europe, I understand that there are these markets being developed for, and IEA has been promoting them, explaining what they can deliver in terms of resiliency and reliability to the European grid. And here we have virtually nothing going on. However, if you go to the Georgia Solar Conference on October 10th at Candida Building.
I'm out of time, sorry.
Well, send Stephen. There's there's going to be a presentation called Electrify Everything. And the fellow who's organizing that is trying to develop markets like this in the Southeast, which is very hard given our utility regulatory standing, but still the company he owns, Don Moreland, is called Solar for All or something. Anyway, that's not quite right. Solar crowdsource, something, yeah. Solar Crowdsource, I think, is his company. And so he is trying to get people in the Southeast to think about these packaged systems.
Mhm.
Have you not heard of anything?
Well, actually, the interesting thing is like way back 10 years ago, when the first Siemens Energy came out, Ford actually had a bundle where you could actually charge, I forgot what they called it, not charge for life or charge green. You basically were able to add as an option a solar array that would be installed in your garage, and you could basically plug it directly in. And so you basically, some would be an offset, basically. But they basically said, yeah, we realize that you might get dirty energy. It's still not clean. If you really want it clean, we include a solar array from SunPower. I forgot the size, exactly what it was, but they had an option, but hardly any takes. So that option disappeared pretty quickly. We have not included these. We basically look at like, okay, everybody buys the components. Somebody's bundling it. I know my mother, for example, in Europe, they basically, she has still have a gas stove, and basically new buildings, no gas stoves anymore. But even when you bundle it, it does make sense. There is a payback, but unless the utilities start changing something in the rate structures, or the local government says like, we need to do something, you see the numbers here. You talk about hundreds of dollars, maybe maybe 1,000. Best case is like $1,000 plus of savings, or a couple $1,000 savings. And you have still much cost that you saw, like for these even bundled systems, they cost a lot. The best, sorry to interrupt you for one more thing. The best thing we saw in the Mel 1 was actually the water heater. If you had a combined water heater and heat pump, that was the biggest return on investment in 3 years back then.
So there was a system that some faculty and students put together at the University of Delaware, where they sold regulation services to PJM from plugging in Nissan Leafs that the students managed. It was really a fantastic idea. So if we had a wholesale market in the Southeast where you could bid for some of these ancillary services, that would make such a difference. And there's discussion about that. So, maybe in the future.
Yeah, if the rates.
That would give you more for the assets you're providing.
If the price for us as homeowners, delivering electricity to the grid goes up, then it makes much more sense. Right now, or if somebody's demand, if somebody says, we want this, then it makes perfect sense. And I don't know, but in other localities, there is more demand for that kind of stuff. So you see the paybacks being better in California than here because the structures are so high, etc. And it's we actually rent these also for industrial facilities when they start doing power stuff, then it becomes a different story. But overall, right now, despite what we're talking about, the Southern companies really, really dirt cheap, and they're not really paying much. They want to sell you expensive, but they buy back cheap. And so and even now the utilities, this is why the car companies are starting to look at it. It's like utility companies say, hey, we like to get these EVs on the grid. It's really good. National Labs, look, it's how much energy we can save. And then in terms of electricity and the companies are like, wait a minute, what are you doing with our batteries exactly? What is exactly going on? And we need to know what value we're providing you because we feel there's something smelly here. I'm being very facetious, but that's basically paraphrasing what is going on a little bit, that people now start not waking up. It's a little more critical question, like, why are you so eager to get access to these EVs? And it must be worth something. And just as you say, Marilyn, maybe there is a better market, and maybe it has to go to a bidding auction process and go, you want this? Pay for it.
So I think this is super interesting. You've been working on this for a good long time. You've been working on it well. You have multiple collaborators. And you're still, I would think by this time you would come up with a really good model. Like, here's what people should do. This would really benefit homeowners. It'd be great for the environment. And you do not find that. And it's not just because of Southern Company. It's not just your Atlanta example. It's your Phoenix example. It's your wherever it was in California example. It's just not, it's got some benefits, but they're small.
18,000 over 20 years.
Yeah, but you put in 0 discount rate, which is just,
Right,
excuse me.
It doesn't. Yeah, it doesn't need stuff.
No, these things never pay off, is what the actual answer is. It never pays off. People think it does, it doesn't, and so you shouldn't do that. You should put in a halfway decent, super low, put in 4%. They will never pay off. So that's interesting. That's a nice result. Thank you very much. More people need to know. This is not an avenue that's gonna go.
Yeah, I would say kind of agree. It's like, unless you really say, if you're in for it for the money, you're not gonna, as a single homeowner, you're not gonna really save much. CO2, you'll save some CO2, but even there, it's like, not driving is better than.
So much, we need to just down our demand and be healthier and happier.
So less kilowatt hours used, 1 kilowatt hour
So
not
much
used
easier.
saves you 3 kilowatt hours, right?
Yeah.
Probably. So yeah, that's the depressing end message here.
It's not depressing, it's fabulous. The truth will set you free. And that's it.
But we do see, like, there have been, the one thing that we do see over these 10 years is that these rate structures are changing. Atlanta had also rate, that was it. Now you see, like, there's the nightly EV rate that Georgia Power for a while had for 1 cent. It sounded really good, 1 cent. And then you started adding in the flat fee, like, that's not really 1 cent anymore. It's actually more now. But you see those things starting to pop up, something that, and coming back to read it, if you start seeing like more like, okay, do we put another vocal plant online? Or somebody starts to wisen up and say, do we really want to put another vocal plant online? Or is like put a little more solar array in a city where we have plenty of solar anyway, and plenty of rooftops. Put the money on the solar, put the money on the nuclear. Again, they're both kind of like CO2 free, arguably, but we all know nuclear is extremely expensive to build. So yeah, you're right. You're looking for policy changes in many ways. And people saying like, I want to do a different lifestyle, but the money is not there right now, at least.
And if you introduced a CO2 tax, the CO2 savings is still pretty.
We haven't really included that. That's when you sort of like, again, it starts affecting the rate structure.
A tiny little.
Yeah.
You'd have
Another
a huge tax.
That's fine.
Well, you look at actually, we have the CO2 avoidance. Here you talk about this CO2. These are the annual CO2 savings. If you look at a kilowatt array, if you have a 10 kilowatt solar array, we say 5 is a sweet spot, 10 kilowatt. The most you save in Atlanta, actually Phoenix, in CO2 avoidance from the grid, 3,800 kilograms.
That's 3 times. So
3 tons. You know what you do when you burn 1 gallon of gasoline, right? That's 20 pounds, right?
Yeah.
10 kilograms. 10 kilograms of CO2 for 1 gallon. You fill up your car with like 20 gallons of gasoline, you got 200 kilograms of CO2 right there.
Well, our footprint is about 16 tons a year. It's not it's not insignificant.
No, it's not insignificant, but it's not insignificant. And again, if you start scaling it up over like a customer base of vehicle owners of say like, millions and millions of people, now it starts adding up. You do get to the gigatons eventually. But that's the tons, so it's 3 tons, or if you have like that's Phoenix, Atlanta, that's 3 tons, it's 3,800 tons, but you see Portland, only 400 kilograms because they already run on hydro. So it's a clean grid, so it doesn't make sense. And that's kind of the biggest message. You really have to, like Valley would know with LC, life cycle analysis study, like locality. That's basically like what is important here. What you do in Phoenix does not necessarily make sense in Atlanta, does not make sense in Portland, does not make sense in LA. You have to tweak these systems. That was like the biggest thing this model we're really getting to. We're not trying to like brushstroke the United States policy. It's like, okay, here's what locally happens, and you can make local savings decisions, and they can be radically different.
And there's one other thing in the first slide or two, you discarded microgrid, home microgrid, sort of neighborhood microgrids. And then at the end, you said something like, this might be viable for fleets, though. So wouldn't a neighborhood microgrid sort of mimic what a fleet operation might be?
Could be. The thing is, though, when we looked at this is the MEL4, the 10-house microgrid. We looked at like if you had these houses become like a My Energy Lifestyle 1, they added a 5 kilowatt solar array, and then we did the microgrid. We found out that whatever they did as a retrofit to the house, smart appliance and a solar array, that had much more significant savings than becoming a microgrid. Now, when you talk about commercial, one thing that is happening that if you have higher loads and you need more at peak, then it might start to make a little more sense because you get economies of scale potentially. Individual homeowners and just stringing individual things together that disjoint may not be, that was then. This is like now we're talking about, what was the year here? 2017. Didn't really make much difference. Now, the difference is with a commercial building is that's why I said employees show up with their EVs. You could maybe ensure that the electric vehicle actually is there during peak demand hours, during peak hours in the afternoon. Because if you right now, if you drive an EV, Mike, you're not here if they have peak time of use rates because you're not home. Your home is putting on. Now, arguably, you can also run the AC lower so you decrease your load. But here we're in a building, and my building where we came out, I had my coat on because like freezing in there in the MRDC building. They're running a load, even though it's load balancing. But maybe there makes sense to sort of have the vehicle. But we don't know yet. And again, if the company buys the vehicles and says every 3 years we're going to buy a new vehicle on lease anyway, maybe they don't care really about battery degradation. So there's all these things that what ifs that we can explore. We have not gone to commercial grade levels. Let's say, okay, you got big loads of electricity, limited roof availability for PV. That was actually China. You had an apartment building. There's no room for photovoltaic on the roof. What do you do then? And do the EV maybe? Actually, Mel China was interesting because one of the reasons to look at that was like making the electric vehicle part of the building, because now people actually got access to a car, because in China in those days you had to basically be on wait for getting a car. If you wanted to buy an electric vehicle, you jumped the line, and so you could get a car as a as a Chinese citizen, you could actually get a car. What if you had an apartment building that already had the cars as part of, as like a washing machine, now you had the car there as common use, what we're saying. So there was like a lot of like, not just like monetary benefit, but also like, I can have access to a car now that I couldn't have. How much is that? Well, it's an intangible thing again. So that's why I say microgrid, you have some savings, but still, like I would say, like I was like, whoop-de-doo, not a big deal. But people in those days were making big deals about microgrid, like, well, we don't see it. But if you have a very, very fine-tuned microgrid, like maybe Marilyn will be talking about, a very fine-tuned with buildings exactly doing the right thing, these numbers might go up. And different story.
Left field question.
Mhm.
You alluded to it a little bit, and that is that you had someone who's got a system and their immediate reaction was to boost their hot water production in their hot tub.
Rebound there.
Is there any consideration for making that thermal energy that's in the hot tub part of the system? So I had a ground source heat pump that had a de-superheater that gave me all the hot water that I wanted during the summer. In my basement currently, I've got an air source heat pump water heater. I've got a dehumidifier and I've got a chest freezer. So I've got two heat producing things and a heat condensing thing all in the same airspace. But they're using air as their medium of exchange, which is really, really inefficient. So could we work with the appliance manufacturers to get de-superheaters installed in my refrigerator, in my, heat pump, in my whatever, and so that we could just
So
exchange that thermal energy?
short answer, the current model, no, it's primarily focused on electricity. But when we went to the 2014 MELF 2, we actually, the original Miner's lifestyle model assumed a very standard classic HVAC system that I was like, this doesn't make sense. It's like all weird. And we did actually bring in the electrical water heater with heat pump combined system that I think Beam started coming out with those in those days, first time. See what that would do. But again, it was focused on like how much electricity am I paying. We did look at like how much gas, a little bit gas are we offsetting here. Right now, when we actually stripped out, also when you do the EV, we kind of stripped out the whole gasoline avoidance and embedded energy. That was in the original My Energy Lifestyle. There was like these embodied energies of the gasoline and stuff that was in there what you're saving. We kind of got rid of that. So the short answer, no, but we did dally in that. But it gets, now you have multiple energy streams. And now you start trading off, okay, what's cheaper? Natural gas, electricity. And if you open that thing, this is why in Atlanta, we actually do, and it comes back to the loads. Because basically you're saying like, if I start switching to natural gas for heating, then the winter load of electricity drops. And you see that that's in the models. You see that that's actually like the winter heating in Atlanta is completely different than say in middle of nowhere, Minnesota, where you have electricity or maybe some even fuel. It starts, Detroit will say like, oh, we run on electricity to heat it. Right. Different story than in Atlanta. So the loads start affecting that. Short answer, no. We did dally a little bit, but that's a whole lot of ball of wax. And that brings in like, again, like what is the payoff of those systems?